Okay, so how are y'all doing? I just took my SAT. I forgot my calculator, but don't forget your calculator. Please make a mental checklist or a physical checklist for that matter the day before you take your SAT. And second, go to church. So we're going to be calculating the electric field at point P due to the semicircular ring of charge. The stats boy doing calculus. So electric field is a vector. So it has a magnitude and a direction. So the first thing I do is I assign a positive direction, which I set as down, and you'll see why. Because this point P, it is exploiting some symmetry here. So agree with me that this ring of charge can be separated into infinitesimally small charges. And each of those charges are going to exhibit some electric field at this point P. However, since it's at the center of this semicircle right here, the x component, say we have this differential charge dq here, and I have another one right here, those x components are going to cancel. So for all of those charges, infinitesimally small charges, all of their x components are going to cancel. However, there is going to be a y component of the electric field at this point P directed downwards. Electric field goes from positive to negative, so away from positive, so at this point it's going to be down, right, away from the positive. So what I like to do is, first I'm going to consider the differential electric field first, so emitted by one singular dq. So, you know, the algebraic version of electric field is E is equal to 1 over 4 pi epsilon naught times q over r squared. By the way, this thing has a radius of r, if you couldn't tell. If we make this infinitesimally small, we go dE is equal to 1 over 4 pi epsilon naught. This is just Coulomb's constant, by the way, rewritten differently. You'll see why. dq, differential charge, right? We broke it up into infinitesimally small pieces, r squared. And last but not least, we need to take care of the symmetry here. So since only the y component is dealt with in this case, we're going to say that the net electric field is only going to be the y component. All right, to clear up some clarity on why I threw in the sign of theta, let us redraw this whole thing again. And point P right here, so let this be r. Right, so this was positively charged, so positive charge. Okay, cool. So I drew my differential charge right here, and I bet that's going to throw some people off. So let's say if I drew right here, dq. And so we can draw a nice little right triangle right here. Now, if this is theta, then the only component of the electric field, so the electric field is going from this charge positive, right? So it's going to go this way, and it's right triangle kind of deal, so we have a y component and an x component. So this y component is dealing with the opposite side, so yeah, that's why we're dealing with sine. If you want me to keep going, let this be the adjacent opposite, and this is the hypotenuse, so sine of theta is equal to the electric field in the y over the net electric field. So the net electric field sine theta is equal to the electric field in the y. And you can substitute in all of that crap in for d, since like you said E is this, and turn it into a differential is equal to k dq over r squared. Right, so you plug that in here, and that's why our integral is going to correspond to this stuff and sine theta thrown in the end. So, yep, which in this case is going to be sine of theta. So what we're going to do here is we're going to end up by adding up each of the electric fields emitted by each of these differential charges, and that's going to break out a bad boy integral, right? Okay, so first we need to consider charge. That is an intrinsic property of matter, and that means we can do something with density with it, right? So as there's a linear mass density, there's also a charge density, linear charge density, charge per unit length. written as so. But we're talking about differentials here. So this is going to be lambda is equal to dq over per unit length. If we break this up into infinitesimally small pieces and consider the length of each, since it's in a circle, we can say ds, where s is arc length, so differential arc length. Now, what is this differential arc length? Well, agree with me that arc length is equal to r times theta, where theta is in radians. So we can talk about differential arc length by doing ds is equal to r d theta, right? The r stays the same at any point in the circle, and you're going to need that ultimately to calculate arc length. So the thing that became infinitesimally small for a differential arc length is theta. So we can plug this in here for ds. So lambda is equal to dq over r d theta. Multiply both sides by r d theta. We get r lambda d theta is equal to dq. Whoa, cool beans, cool beans. Right, so now we can plug this in to dq for our differential electric field right here, right? So that's going to be dE is equal to 1 over 4 pi epsilon naught. Now this is dq, r lambda d theta over r squared sine theta. Okay? So first thing, I'm going to rearrange this to prepare us for our integral. Right? So the first thing I'm going to do is I'm going to divide out one of these r's, right? So I'll rewrite this over here. So this is going to be, and I'm going to move all the constants to this little fraction right here. So 1 over 4 pi epsilon naught r, right? Since we divided this r into here, so I just move the remaining r over here. And then now lambda's on top, so this is no longer 1, this becomes a lambda. And then we have sine theta. I'm just going to move the d theta over here. All right. We are ready to take the integral. So we're going to integrate with respect to theta. So E, now it's the net, is equal to lambda over 4 pi epsilon naught r. Note that this is a constant. I can pull it out of the integral because it's not changing. I don't really care about it. And then integral sine of theta d theta. So what are our limits of integration here? So an integral is basically a fancy plus sign, right? You're adding up all of these dq's, right? But as you add up these dq's, you notice that there's an angle involved, right? So you're going to integrate this thing with respect to theta going from 0 degrees, and then you're going to add up all those bad boys all the way to pi. We're using radians. So 0 to pi. Right? So, and then we evaluate our integral. So E is equal to lambda over 4 pi epsilon naught r. So a derivative of a sine is a cosine, so the integral sign is a negative cosine, right? So negative cosine theta evaluated from 0 to pi, right? So that's just one way to check. You do a derivative, so this is going to be a cosine, but the integral's opposite of derivative, so yeah, negative cosine. Anyway, so, and then we're going to plug in our limits of integration, right? So we're going to go E is equal to lambda 4 pi epsilon naught r. So I'm going to plug in the final value, so negative cosine of pi minus the initial value. So minus cosine of 0. Whoops. Right? Whoops. FaceTime calls are a thing, so I had to end the video because the thing was like blah, blah. But okay, so continuing to plug in your limits of integration for an integral right here. It's going to be E is equal to lambda 4 pi epsilon naught r evaluated from, so we're going to do final minus initial, right? So negative cosine of pi minus negative cosine of 0. So pre-cal, unit circle, haha. Okay, so this is cosine of pi is going to evaluate to -1, so -1 times -1 is just 1. And the negative times the negative is a positive, so plus cosine of 0, which is 1. So, yes. 1 plus 1. I'm stuck. So this is going to become 2 lambda over 4 pi epsilon naught r, which is going to simplify to E is equal to lambda over 2 pi epsilon naught r. And that's actually a variant of the answer, but I'm going to reduce it all the way down to get rid of this lambda, so we can only have it in terms of these constants r and q. So what is lambda? In consideration of the whole thing, it's the total charge of the thing, q, over its length, which is going to be its arc length. So what is the arc length of the whole thing? Well, that's going to be s times the radius of r. Oh, s is equal to the radius of r times theta. So theta is pi, because 180 degrees, right? So substituting that in for arc length, we get lambda is equal to q over r theta. We plug this into here for our final answer for the electric field. So q over 4 pi squared epsilon naught r squared. So that is our net electric field at this point. We can check our answer here. So let's say the charge, we can put a limit on this, let q go to infinity. As the charge becomes infinite, yes, the electric field becomes infinite at that point. Makes sense. And let's say we put this point infinitely far away from this thing, so put a limit as r approaches infinity. Then we're going to get electric field becomes 0, which is true. At infinite distances for point charges, for these collection of charges, these differential charges, the electric field is going to be 0. So yeah, that is how you calculate electric field due to a ring of charge. Peace!